In this segment, we'll wrap up our discussion of the goals of software design with three final goals: reuse, testability, and division of labor. Let's start with software reuse. The idea of creating software by simply plugging together off-the-shelf pieces the way one can with chips in digital electronics has been a long-standing dream, but one only partially achieved. Now, that said, much routine and repetitive work in software is done by using pre-written library code, and this greatly improves software productivity. In object-oriented design, pre-written code comes in class libraries of standard classes for things such as collections of data, like lists or maps, standard activities like GUI and network communication, sophisticated mathematical tasks like arbitrary precision arithmetic, and so on. Java has what is widely recognized as one of the finest such class libraries, with thousands of classes. And the Java libraries have an excellent object-oriented design, so we'll use them as examples in some of the object-oriented lectures to come. Now, designing a class library, a good one anyway, is difficult. In many ways, it's the highest form of software design. A class library must anticipate the needs of many different applications and have methods and interfaces that are flexible enough to satisfy them all. Plus, it must be easy to understand, since many developers will have to learn it. This challenge is a close cousin to making software modifiable, but it has the added element that as many as millions of developers and hundreds of thousands of different projects may use your work, so every decision matters a great deal. For the same reasons, CPU and space efficiency, while always of interest, are even more critical in a class library. The Java collections classes, which are a subset of the larger Java libraries, offer a good example. A collection class is a class that contains or collects other objects together. A list, array, stack, or queue are all examples you may have encountered in other courses. When you design a class to hold a collection of objects, there are a number of trade-offs to be made. Is it okay, for instance, to just hold the objects in any order? Or must they be in some specific order, as in an array or a linked list? Is it okay to add two equal objects to the same collection, or must they all be unique? And do you need to search the collection quickly for any object, or is it enough just to be able to go through all the objects in it one at a time? The collections class library solves this by defining several different related kinds of collection. We'll look at a number of them in detail when discussing object-oriented design later in the course, but they're worth a brief overview here. The simplest type of collection, class in the library, is a collection, that's its official type name, and it provides only bare-bones behavior. You can add and remove objects, you can go through all the objects in the collection, and remove objects actually, but that's about it. Now, if you want the objects to be held in a specific order, and to directly ask for an object by its sequence number, add this as the 4th item, find the 10th item, and return it, then you use a list. And if you want the collection to refuse to hold duplicate objects, then you use a set. And if you further want the collection to keep unique objects in sorted order and let you retrieve them in order, then you use a sorted set. Now, importantly, these types of collections are all related via the mechanism of inheritance, which we'll get much more detail on later. And that means that code that works with a collection will work just as well with a set or a list, since those two more powerful collection types provide all the bare-bones behavior of a collection as well. And code that works with a set also works with a sorted set for the same reason. A sorted set does everything a set does, but adds sorted order. This kind of fine-grained choice of behaviors with interoperability between types is characteristic of good object-oriented library design. Now, in lecture question 1, look up hash set and tree set either by simple Google search or in the Java API docs, to which the Google search will almost certainly lead you. How do those two classes fit in with the system just described? They're part of the collections class, but we didn't mention them directly. Now, don't try to understand all technical details in the documentation just yet. The main point is to see how these classes fit in with the types that I just mentioned, and what is different between them. Why is there a hash and a tree in their names? By the way, you may find it useful to know that they're in the java.util package when you look them up in the Java docs. So returning from a pause there, they are both sets. But hash set implements the set behavior using a hash table, and tree set uses a binary tree. And here's a brief aside from the transcript, by the way, just showing how I got that information when I tried answering the in-lecture question. This is a display of the Java API documentation. And up in the upper left corner here are packages. So as I mentioned, java.util is the package in which this collections class appears. And if we look down under classes, I found hash set here. And looking down in here, it does indicate that the thing is backed by a hash table, which is a sort of fancy way of saying implemented by a hash table. And then tree set, similarly, is described as being implemented by a tree map, at least, which is a sort of complicating detail. If you look at tree map, then it talks about it being implemented, in fact, by a red-black tree, which is a special kind of binary tree that is maintained in balanced form. Again, as I said, the details are not critical at this point. The question was mostly designed to get you a little familiar with the collections class documentation, and we'll be looking at this more closely in later lectures. So, in summary here, the collections class library provides different and interchangeable implementations of the various types of collection. So you can select the implementation you want, in the case of set, obviously, a hash or a tree, and can later change your choice without affecting the rest of the code. Now, if you read between the lines in that admittedly dense API documentation, a tree set also qualifies as a sorted set, since a binary tree keeps its contents in sorted order. And that leads us to question 2. If a tree set is a kind of sorted set, then I should be able to get the first element in sorted order from it. What method does that? And obviously this is an incentive to go look at the methods of tree set. Once you're looking at those in the docs, how do they relate to the methods of collection? Returning from a pause there where you might have done that research, the answer given here, and we'll also look at the docs briefly, is that the method is first, and the methods of tree set include all the methods of collection. This is as expected because a tree set is a type of set, and we said that a set can also work as a collection. And then following up on the promise to look at the docs here, if we go to tree set and look at its methods, there are quite a few of them. You can add all of another collection. You can clear the thing and empty it. You don't have to understand, again, all of these just now, but there is one that's pretty straightforward, and that's first, returns the first or lowest element currently in the set. And it goes on, iterator, size, returns the number of elements in the set, and so on. Now, if I now go up to collection, which is actually linked from here, there's collection, and look at its methods, every one of these is also in the tree set collection. Not all the tree set methods are here, but all of these methods are in the tree set. So, as you may already know from earlier courses, in an object-oriented design, this type of relationship, where one class extends upon the methods of another, is declared via inheritance or derivation, a concept we'll return to repeatedly in the course. Tree set derives from collection, and from set and sorted set as well, by the way. And thus it has all the methods that collection has, and more. So our next design goal here is software testability. And the first sentence says a lot there. Large software systems are difficult to test, which is a bit of an understatement. There's several reasons. First, it's hard to design test cases that can reach all parts of the code, especially when certain parts are only called at the end of a long chain of function calls that must first pass through other layers in the software. It's perfectly common for the trace of function calls leading up to a bug in a large software system to be 100 levels deep, which means that the bug occurred only when function F1 called function F2, called function F3, all the way out to called function F100. It can be hard to reach through the many layers and test code effectively. And second, since there will be a large number of test cases on a big program, testing takes time. Most testing must be done then not by hand, but by automated tests. For some programs in which high reliability is essential, for instance commercial avionics or medical devices, there may be more code written to perform tests on the program than code for the actual program itself. And third, even if the testing is fully automated, it may take hours to complete. Hours for the machine itself to do the automatic testing, in other words. And you don't want to repeat such testing for the entire program when only a part of it has been changed. Now, the solution to these problems is to break large code into pieces, no surprise there, and to independently test each piece. And this is termed unit testing, and the pieces are sometimes called test units. Unit testing lets you call functions in a test unit directly without having to negotiate your way through 100 other calls that lead up to the test unit. Unit testing aids automation, since there are good libraries available to build and to run unit tests. And unit testing lets you repeat tests only for the test units that have been changed. So the same careful compartmentalization of function that makes big software easier to comprehend and to modify also makes it easier to test. And question 3, do a bit of a web hunt and find the most popular library for unit testing in Java. And per usual, I'm not asking you to understand how to use it just yet, we'll get there, but just know what it is. There is a clear winner, and like I say, it's one we'll use later in the course. Turning from that hunt, the library I have in mind here is JUnit, which is by far the most popular system for testing, unit testing, Java applications. And then our final design goal, division of labor and expertise. A big software system spans many areas of expertise, both technical and otherwise, non-technical. A major website, like Amazon's or Google's, uses many different programming languages and requires expertise in high-volume databases, high-performance distributed web services, browser-embedded UI for the actual page, supply chains, it is, after all, a retail outfit, tax law, artistic aesthetics, data analytics, information security, and so on. And the main point then is that no one person is expert in all those areas. And once again, a careful division of the software into well-defined interacting modules is the solution. If we define a data storage module with a clear interface, we can hand its implementation off to experts in that area without anyone else needing to even understand their implementation, as long as it's clear how to use it. If we define a sales tax module, we can hand it off to experts in accounting software and tax law. In case it's not obvious, by the way, sales tax is surprisingly complex because it varies by municipality and product, sometimes differs from one side of the street to the other, or by the details of its packaging of the product. Now, there is a classic design pattern that illustrates this point well. Software that presents a graphical user interface to the user usually separates the code into 3 major parts. One for drawing the interface, which is the view, one for maintaining the underlying data and logic of the application, usually called the model, and one for responding to user inputs and actions like button presses, and that's called the controller. The code that displays a list of products with pictures, and prices, and buy buttons is separate from the code that tracks inventory and prices, and from the code that responds to user clicks on links and buttons. This is usually termed a Model View Controller, or MVC design. And it works well because different kinds of expertise are needed for the user-facing view and controller versus the model that underlies the view. In our example, an MVC design would let experts in user experience and aesthetics do what they do best, and experts in large databases and accounting do what they do best. So a final bit of summary here. There are other goals of software design, but these last 3 segments of lecture have covered the big ones. Design is about reducing complexity cost, communicating about software, making software comprehensible and modifiable, designing easily reused libraries, making software testable, and dividing software into different parts requiring different expertise. Now, in the next topic, we'll look closely at the language features that enable all of this in Java.